All right, good morning, everyone. I'm going to skip this. Well, yeah, we can just go through kind of the important thing here with all the theorems and conditions. Okay. So extreme value theorem. If a function is continuous, so this is the only condition that EVT needs is continuity. And it has to be on the closed interval brackets. Then we can guarantee that there is both an absolute max and an absolute min on the closed interval from A to B. Okay, so we test critical points and we test endpoints. Right? Those are the only candidates that we have to worry about with absolute max, absolute min, and then you're only providing y values, right? These are y. Mean value theorem and Rolle's theorem are very much alike, but there's an additional condition besides continuity. There's also differentiability. So function has to be continuous on the closed interval bracket, and differentiable means a smooth curve on the open interval, parentheses. Then there is at least one point C on the open interval. Whatever guarantee that we find has to be between the endpoints, where the slope between the endpoints, right? And this is where we have to take the time to find the order pairs at the endpoints, find the slope, and we set that equal to the derivative. Okay, Rolle's theorem, very much, virtually, it's the same theorem. We just have a very specific slope that we're looking for, slope 0. Okay, so continuous on the closed interval bracket, differentiable on the open interval, parentheses. We are still finding endpoints, but the endpoints have to be level with each other. That's the only, that way we can guarantee that there must be a slope 0. Once we guarantee slope 0, we set that equal to derivative. By the way, you guys have a key attached to your morning review, so you can definitely work ahead if you like, or just check your answers that way. Okay, number 1. We have f of x given by this function here on the closed interval from -2 to 2, determine the max and min values. So this is applying extreme value theorem. The only condition for extreme value theorem needs to be continuous. We do see a variable in the denominator, which could be a red flag, but if I set that equal to 0, I'm going to get imaginary numbers. So we know that there's not a vertical asymptote we have to worry about, right? If you set x squared plus 1 equal to 0, you get x squared equals -1. Square root of negative is undefined. So we know our function is, we know this is EVT. We know our function is continuous on the closed interval. Okay. So now we know that if it's extreme value theorem, our endpoints could either be at -2 or 2, but it could also be at the critical point. Okay. So we know we're going to be testing our endpoints, but let's just go ahead and find some critical points as well. Critical points comes from the derivative. And once we find the derivative, we set the numerator and the denominator of the derivative equal to 0. This is quotient rule, numerator and denominator. Sorry, 2x. Okay, f prime g minus f g prime all over g squared. Let's do some cleanup here. We get 2 minus 2x squared. Okay. We set the numerator and denominator equal to 0. Let's see what happens from the numerator here. We get 2 equals 2x squared. X equals plus or minus 1. Here, we know there's nothing going to be here. If we take the square roots, we get x squared equals -1. Okay. Yeah. No imaginary numbers to worry about here. So just 1 and -1. All right. Are we going to include both these critical points? Are both these critical points valid for our problem? Are we going to test both of these? Yes, because interval, right? We always are going to look at the interval to determine if they're a valid point. So we have 4 points to test. We have 2 critical points, 2 endpoints, and they all get inserted into the original function, right? We're looking for location now. We're looking for position or height. Okay, -2 in for x, get -4 over 5. Insert -1 in, we get -2 over 2. Insert 1 in, 2 over 2, which is 1. Insert 2 in, 4 over 5. Okay. We know the highest and lowest values are just restricted to these numbers here. Highest number I see is 1. Lowest number I see is -1. Questions here? All right, number 2, Rolle's theorem. Okay, we know we're dealing with a polynomial here. No denominator in the variable. We know our first two conditions are good to go, but we have to state them. Okay, we're always going to find the endpoints. Don't find a derivative just yet. Into the original function, we get -2 minus 3, -5 times 0. Anything times 0 is 0. Enter 3 in, we get 3 minus 3. That's 0 times 5 squared, which is 0. Okay, we know that these order pairs are directly across from each other. There's a horizontal line that is drawn between these 2 points. The horizontal line is slope 0. So we can now guarantee a slope 0 somewhere along this curve. Okay, so I want to find the derivative. I could go through product and chain, but I think this is easy enough for us to just expand out, right? Maybe it takes a little bit of time here, but if I fold this out and distribute that through, I don't think that's too bad. Let's just do that. Let's just expand this out. So I'm going to keep that x minus 3 for now. I'm going to expand or FOIL that x plus 2. Make sure you write this out twice, right? That's x plus 2 times x plus 2. Okay, that we don't just distribute the 2 through, because we do that, we're going to miss out on some of the terms. So x squared plus 2x plus 2x plus 4. Okay, expanded everything out, makes it an easy power rule problem. F prime. Set f prime equal to 0, right? Rolle's theorem, slope is 0. Factor. Okay. What are our C values? Do we get to keep both of these? Okay. -2 is not inside the interval, right? We can only keep what's inside the interval. -2 is out. Okay, number 3. Mean value theorem. Polynomial, no issues. It'll pass both conditions. Okay, test the endpoints. Zero. -2. All right, we have to find the slope, right? We're trying to guarantee a specific slope. This is mean value theorem. Change in y over change in x. So we know that somewhere along this curve, there's a slope of -1, right? And we're trying to find that location now. So I'm going to just clean this up here, just so that I don't have to go through product rule. If I distribute this through first, I can just rely on power rule. Okay, so here's f prime. My slope is -1, so I want to insert my slope into the correct location, right? I don't want to enter -1 in for x, right? This is slope that I want to guarantee, not the location. Okay, -1 equals. All right, careful how we do this, right? If we're trying to factor or solve, we have to bring everything over to one side. We got to get that 0 to show up before any factoring solving can be done. Okay, so bring that -1 over to the right side. Solve for x. Okay, are both these locations valid? Okay, one is outside the interval, right? It's got to be between.
For brackets, it doesn't have to be outside, right? Or there's one is worth, right?
As long as the only bracket we have is with continuity, so the function has to be continuous on the closed bracket, differentiable on the open, but then when we find our C value, it's on the open interval.
All right, but for EVT, which doesn't matter.
Oh, right, EVT, it doesn't matter, right? EVT, because we're testing endpoints as well, endpoints could end up being the max or min. Right. Yeah, but roles, the mean value theorem, our solution is only between the interval. Okay, number 4, this is a good practice for us to create our graph based off of f prime. So this is the f prime graph. We just want to sketch a possible graph of f of x. So remember, let me highlight this graph a little bit here. And then up here, it just flattens out. This. Okay, we can label what we're looking at here. Above and below the x-axis, positive slope, negative slope, slope 0. So if I want to create my f prime graph, I'm always going to target my x-intercepts first. Endpoints from 0 to x-intercepts 1. Yeah, these don't land very nicely here, so you can pick any number. It really doesn't matter. So I'm going to say this is 2.9 and this is, what, 5.8. But that's not that important. As long as you, whatever estimation you come up with, that's valid. Okay, don't look at the movement of the graph, look at the location. Is it above or below the x-axis? If it's above, we want to assign that interval as positive slope. If it's below, we want to assign that interval as negative slope. Okay, between 0 and 1, we see it's below. Between 1 and 2.9, it's above. Between 2.9 and 5.7, below. 5.7 to 8, above. If I want to create my second derivative sign line, where do I look? Yeah. And what do I place onto my sign line, though? Peaks and valleys, right? Max and mins. So there's my POI, there's my POI. Okay, there's nothing here. There's a sharp turn there, but that's not a peak or valley, so we just leave that alone. It's just these two right here. Two and 4. Now we look at the slope, right? Positive slope means concave up. Negative slope, concave down. Positive slope, concave up. Sketch a possible graph. Okay, let's create 2 versions of this graph here. Or not 2 versions, but 2 drafts. First, just look at this. The location right now doesn't really matter. There's nothing, no information given about order pairs. So all we want is a relative min at 1, relative max at 2.9, and a relative min at 5.7. Okay, so wherever that is, that's fine. So at 1, I'll target a relative min here at 2.9. I'll target a relative max somewhere here. 5.7, I'll target relative min. Okay, so okay, so I'm just making my graph look like the shape and pattern of my arrows. Down, up, down, up. We go back now. We're going to improve on this graph based off of the second derivative sign line. We know 2 and 4 are points of inflection. So wherever the graph lands at 2, wherever the graph lands at 4, so this is concave up. This is concave down. This is concave up. Now here's something different here. You won't see this on the test, but just want to kind of show you real quick here. What's here? It's holding a constant number, right? What's that? What's this number here? That's a y value of what? 1. This is the derivative graph. So what does that mean? That means a slope of 1, right? Slope of 1. What does slope of 1 look like? Just a straight line, right? Slanted line. So the graph is going to look something like this. Right, it's neither concave up nor concave down. It's just going to be a slope of 1, right? All these are slope values, and yeah. So just want to show you what that looks like. Okay, next page. Again, a derivative graph is shown. Go ahead and mark up your graphs. Let's create our slope and concavity sign line to get a visual as to what our actual graph is going to look like. Critical point for f prime is at A. To the left of A is below the x-axis. To the right of A is above the x-axis, so negative slope followed by positive slope. What are we expecting for the original graph? A relative what? Max or min? Min, right? Yeah, so you know the graph is decreasing followed by increasing. Right? Look at the arrows to kind of help you get to the shape of the graph. This is kind of confusing to look at. Right? This is more helpful. So now let's create our second derivative sign line. Maybe it'll help, maybe it won't. But since we have it here, we know that there is a relative max at B, so this must be a point of inflection, right? Increasing slope translates to concave up. Negative slope is concave down. So let's just see what this graph kind of looks like, right? We know that at A, the graph is going to be decreasing, followed by increasing. And then at B, wherever that B is, it's going to be concave up, followed by concave down. And we have some idea what the graph's going to look like, so we'll use this to maybe give us some idea for our answer choices here. Okay, f of x has a relative min at x equals a. True or false? True. F of x has an absolute maximum at x equals b. No, that's definitely not true, right? Now, if you're looking at this graph, you may be tempted to say that, but if you're able to create your sign line and see what the graph actually looks like, you'll be able to convince yourself that this. Okay, so we already know the answer, but let's just go down the list anyways. F of x is increasing from a to b. Yeah, that's true, right? F double prime is positive from a to b. That's definitely true, right? So having these sign lines are so helpful. AP exams as well. If you get that sign line in front of you and sketch some version of the graph, even if it's not completely accurate, you can answer a lot of questions just with that picture in front of you. F double prime has a 0 at x equals b. That is true. That's a point of inflection. Point of inflection is definitely a second derivative value of 0. Okay. Those are our good reviews. Which of the following is true about the graph of f below? So this is the original function. Okay, so now we're looking at the original function. So whatever you see is what you expect. Relative max, relative min, relative max, increase, decrease, increase, decrease. Okay. F prime, slope is positive from D to F. That is true. F double prime is 0 at points B, D, and F. That's not true, right? F prime is 0, but not F double prime. F double prime 0 is probably more like at C and E, right? This is talking about points of inflection, and that doesn't line up with B, D, and F. This is false. Second derivative is positive on the interval from A to B. Not true, right? This is concave down. Again, we're looking at the original graph, so we're able to just look at the curvature. F double prime is greater than 0, concave up from D to F. Yes, part of it is concave up, but then it definitely switches to concave down along the way, so this is also false. Okay, so the only true statement is 1. Number 7. Okay, find the extrema of the function. So let's go ahead and find the derivative, create our slope sine lines, and see what we have. Bring down the 3. Set equal to 0. Okay, basically we're just going through the first derivative test here. I'll test 0, I'll test 6, I'll test 8. Negative times negative, positive. 6 in for x, negative times positive is negative. Positive times positive is positive. Okay, so the graph looks something like this, right? Absolute min, absolute max. Well, we definitely don't have any absolute min or max, right? The arrows are going to overtake each of the relative mins and max, so that's out. Okay, there's relative max at 5, relative min at 7. D. Critical points. Find f prime, set f prime equal to 0, solve for x. Okay, I'm going to skip this one. This is pretty easy here. You can look at the key if you want to try this on your own, but we're just setting f prime equal to 0. That's it. And this is no challenge here. That's just power rule. Okay, I'm going to skip number 8. Okay, number 9. Find the inflection points. Inflection points comes from the second derivative. We have to make our way down to the second derivative. Okay, the algebra is a little messy here, but okay, first thing is I'm going to just go through product rule and a little bit of chain rule here. So product rule. G prime. Outside's derivative times inside's derivative. We got parentheses cubed followed by x plus 4's derivative. Parentheses cubed becomes 3 parentheses squared with the inside intact. Then we multiply by the inside's derivative. This is times 1. Okay, we want to find the derivative again, but maybe it's a little bit easier if I just can clean this up a little bit here. You see how these are, if I treat these like two separate terms, what's the GCF that I can pull from both these terms? Yep, and a 2. It just makes it a little bit faster if I can just speed up that process a little bit. So really what I'm doing is I'm dividing everything by 2 and x plus 4 squared, because that's a common factor that I can pull. So imagine this, we're just dividing everything. We're pulling a 2 and x plus 4 squared out, which is really just means that we're dividing it out. Okay, so if we do that, we can see all the leftovers, right? All the leftovers will go in this space here. So we see that 2 goes away. 3, there's 3x plus 4, there's 2x plus 4s here, so we know there's still an x plus 4 remaining. Okay, with the second set here, x plus 4 squared goes away, x plus 4 squared goes away. 6 and 2 reduces to be just 3x, so speeds up the process a little bit here. And now I have my f prime. Okay, we can go through product and chain rule again, but maybe this is a little bit faster if we just FOIL this out. Let me see. I'm going to put that 2 with the 4x plus 4 here. Okay, I'm going to just FOIL this out. It's not too bad here. Okay, I guess I could have gone through product and chain rule again. Okay, so f double prime. Okay, 24 can come out of everything here. I set equal to 0. So for x, we get x equals -2 and x equals -4. Okay, can we just stop here and say that these are definitely points of inflection? We also have to make sure that there's a change in what? Change in sign, right? So you have to, whenever you find points of inflection, you have to go through your sign line, because there may not be a change in direction, and you may be listing out a critical point that may not fulfill a change in sign, therefore not a point of inflection. So we have to always make sure you double check. Don't just stop here and say that those are points of inflection. Okay, we test this against the second derivative function here. Factored form is good. Negative times negative is positive, that's concave up. Negative times positive is negative, concave down. Positive times positive is concave up. Okay, so that confirms it, that these critical points are points of inflection, but don't just always assume it without testing, okay? And if I want to find the physical locations of these points, where would I find that? How would I find the y values? Back into the original, right? Anytime I'm looking for a physical location, got to go back to the original. Okay, answer choice F. Okay, let's do 11 and 12. I want to skip number 10, 11 and 12. Okay, we have a box. Base is 3 times the length of the width. So let's say this is x, this is 3x, and then we have a height. Construct a box whose base length is 3 times the base width. The material used to build the top and bottom. Okay, so this is a closed box here. We have 6 sides here. $10 per square foot. Material used to build the sides, $6 per square foot. Box must have a volume of 50 cubic feet. Determine the dimensions that will minimize the cost. Again, first thing you do is focus on that word there. What is that word describing? Cost, right? And cost is related to surface area. Okay. Because we already have the volume, so it's surface area that's where the cost of material is going to come from the material that's used to create the box. Okay, let's build the surface area first, and then we can work in the cost. So, surface area is exactly what it means. It's the area of the surfaces. We have 6 areas to find. We have 6 surfaces that we have. Okay, let's start off with the base. What's the area of the base? What's the area of the top? Also 3x squared. Okay. What's the area of the front face? Okay, yeah, we can do that. XH will be the side, so it doesn't really matter. But we do know that, okay, there's XH here, and there's also another XH here. Okay, so we have a pair of XHs and we have a pair of 3 XHs. Six sides, 6 areas. Are we good there? Okay. The top and bottom is more expensive. We know the top and bottom has $10 associated with it. And the sides is a little bit cheaper, $6. So we're going to add those like terms and multiply the dollar amounts into it. Okay, so here's our cost equation. This is 1XH plus 1XH plus 3 plus 3. That's 8XH. Okay, are we okay building that equation? All right, you're not having to memorize any formulas, right? You're just building your surface area just by the knowledge of adding up each of the area. The only thing you have to know is length and width. Yes.
So why can't each side just be XH?
Oh, the reason why is because this face is longer than this face. So you see how the sides is length times width is 3x is x times h, but the front face here is 3x times h. You see how the front's a little bit larger? Yeah.
Okay.
But to your point though, if it said that the base was a square base, then there'll be xh's all the way around. Okay. We want to find the derivative, right? This is the center of our problem. What's standing in the way right now? Yeah, that h, right? Too many variables here. So what help can we use? Volume. Volume is length times width times height. Volume given to us is 50. Solve for h. Now we're going to insert this. Once you insert that in, you're just trying to get it to the point where you can apply power rules. So the 50 over 3x squared gets inserted in for h. Clean that up, multiply that through, pull that x squared up to the top. Combine some of the x's together. You're left with 60x squared plus 800x to the negative 1. So now all we do is we just find the derivative, set the derivative equal to 0, and solve for x. Once you solve for x, you just go back and read the problem and see what are they asking for. They're asking for dimensions, or are they asking for a cost? Okay, so here's C prime. Go through power rule, set the derivative equal to 0, solve for x, and insert. Okay, I want to quickly go over number 12 here. Again, you guys have the key, so you can kind of look at number 12 on your own. Sorry, number 11 on your own. So we have 50 apple trees in the orchard. Each tree produced 800 apples. For each additional tree, the output per tree drops by 10 apples. Okay, so the issue is when you plant too many trees, the resources get strained, and so each tree is not getting as much nutrients as it could be. So we want to find the total output. So there's this element of the more trees that we add, we technically produce more apples, but then each tree is going to become less efficient. So we know it's going to be the number of trees the number of output that's produced, number of trees multiplied by the apple output per tree. Okay, but really you just have to know that there's going to be an addition element and a subtraction element here. So we start off with 50 trees. And then each tree that we add, there's going to be a decrease in the number of apples per tree. So each tree starts off at 800 apples. But then each time we add a tree, what happens? We lose what? This 10 apples. So there's always this, we add something and we lose something at the same time. Yeah. Oh, the 1x is coming from the fact that it says for each additional tree planted. So that means that for each tree that we add, we're losing 10 apples per tree. So now that we're here, there's no need for a second variable, second equation. Everything is self-contained here. We just FOIL this out, find the derivative, and solve for x. This is 800x minus 50 minus 500x, which is 300x. Once you have your equation all cleaned up, find the derivative. This goes away. Always set the derivative equal to 0. So how many trees should be planted? We know that x is 15, so we're going to have to add 15 trees to maximize the output. Once we have more than 15 trees, then we're losing too many apples per tree, and it's just not as efficient. Because we started with 50, 50 plus 15 will be 65. But it's asking for how many trees should be added, so 15 is good. All right, see you guys in class. Thank you.
I'll let you know during.